present us this exciting work.
Thank you, Harry and Shunbo. I really appreciate this. This is wonderful. So the way I've set up this talk is to point out that, you know, today's power systems are completely, the cyber and the physical are married to one another. It's just impossible to have one without the other. And operations require us to use the cyber layer, but what if the cyber layer was attacked? The whole goal is not to talk about attacks. I've done a lot of work in that area, but to talk about all the data that we already collect in the grid. How do we use that in an intelligent manner to not only be resilient to attacks, but to be resilient to all kinds of changes that happen? So can we go beyond some of the simple mechanisms we have in energy management systems? This is joint work with my collaborator and colleague, Oliver Cosset, and our PhD students, Andrea Pinsetti and Zhigang Chu. And these are supported by several NSF grants as listed here. Let me go down here. So very broadly, I think this is preaching to the choir. The power systems is really a complex system. It's also interconnected across literally the North American continent. And you would think about it as, you know, maybe there's not really a hierarchy, but there's still a model of going from generation through the transmission system down to the distribution and very end the consumers. And all of this is managed today by a cyber system which has a collection of sensors and communication systems. And what that enables us to do is bring that data back to control centers that we call EMS, right? Energy management systems, cyber management systems. And you have them at the transmission level. These days you have them at the utility level, which can be called at the Uber distribution level. You have them at the digital substation level and so on, right? And we're moving towards consumers producing and having their own mechanisms to control. So there's a lot of this going on. Yeah, and what I'm going to focus largely on is the transmission system. So in the context of the transmission system, today we manage our transmission system almost entirely through sensing data. We don't send our trucks out there without knowing where there's a problem. And what is done with the sensing data? There are energy management systems, which are really software systems, but are housed at these control centers and operation centers that are continually monitoring the grid 24/7. So the data comes in, it's processed, and a control action is taken. This can happen at multiple time scales depending on generation or load or supply management, right? Now, our assumption here is that somehow the attacker, obviously with inside information, you're talking about nation states kinds of attacks in these cases, has enough side information to know where the data flow is, and it can inject malicious attacks. Let me assure you that if the attacker just injected noisy attacks, the system is very resilient. So what the attacker needs to do is to do something far more intelligent. And the question then is to ask, what is that intelligent attack that the attacker can do, right? So the way we did this was to not just do it in theory like it has been done so far, but to actually build out this energy management system. Now, energy management systems are extremely complicated. They run in the millions of dollars in cost. What we did is we picked 3 core components of the energy management system. We built a status, and we did this with an industry partner who's an expert in power system simulation, Inksys and Power Data, run by Robin Podmore. And we built out the state estimator with a topology processor, and we built a real-time contingency analysis and followed that up with a general SCED model, which takes the contingencies and does a security constrained economic dispatch. So this is our model. We tried it out on multiple test cases. Cascadia system that Podmore has generated as a synthetic data for Washington State. We used the Polish data set, and then we moved on to the Texas synthetic data set that I'll talk about in a minute. So this is our broad model. And this is sort of a visualization of the front end of our platform. And if anybody's interested in running tests on this, just email me. We are giving out code, but on a trusted basis, because certainly there are some, the platform itself is Robin's, and I think that's their business model. Right. So the whole idea was to show 2 things: that you can build out these normal operations, you can put data into it, things work very well, and bad data detector works well when you have noise. However, if you had any kind of a attack on the system, then bad data detector would let it go through, and you would never realize that the system measurements have been changed to actually cause a downstream effect, to cause a line overflow, to cause a post-contingency violation, and bad data will not detect it. So what we've built, and what I'm going to talk about for the bulk of this, is the anomalous data detector that we've built. And the idea is quite simple. The idea is based on the concept of how the attack happens, what kinds of attacks are effective, and how must we design these anomalous data detectors. So let's, for the next few minutes, just focus on how do you design attacks that are effective. As I told you, let's just consider the simplest model, linear model. All of these can be generalized to the nonlinear model, but let's just start with this, right? So what's our measurement model? It is that you get your power injections and your power flows, and what you want to estimate is your underlying voltage, complex voltage states, right? And obviously you get it in the presence of noise. Now, an intelligent unobservable attack is one where I add an attack vector A, which actually lies, which sort of basically moves the state over when you estimate the state, and therefore doesn't appear to be noise. So in other words, I need an attack vector that looks like H times C, all right? And a good attack vector is one where H times C is actually 0, which means that there's no net load change even as you change these measurements. So there's a way to do this, and there's a way to do this even with nonlinear AC measurements, where you would, if the attacker took over a part of the network, it would estimate the state first and then use the state to change measurements. Okay, so that's the very broad picture. I'm not going to go into the details of the attack any further, but let me give you a little story of how this attack would happen, right? Here's your normal operating system model. You get SCADA measurements every 4 seconds, but by the time you're done with these processing, it could be up to 5 minutes, depending on the size of your network. SCADA comes in, you estimate the state, then you go in and do contingency analysis. You take the list of your contingencies, you put them into your SCED, you run your SCED model, and that determines how you're going to run your generators for the next instance. You do that instantiation of control, and you go back in the system, right? What does the attacker do? The attacker is aware of this. Let's take the model where the attacker is full system knowledge. We can actually change that up, and we can do limited models and so on. It still will work, but for the sake of this presentation, let's assume this. So the attacker comes in, it knows how to design this attack vector. And what it does is it intercepts the false data, the data that's coming in and replaces it with false data, right? So the false data is intended to redistribute the loads in such a way that it doesn't look like noisy data to the state estimator. So bad data detector is not going to go off, right? But what the measurements are supposed to do is to actually change the list of contingencies. In fact, literally hide a post-contingency violation. All right, so contingencies based on the spoof data will lead to a new optimal generation dispatch. And that in turn will lead to a dispatch that was not needed on a particular line, leading to a post-contingency line overflow. So in this setup, you do need to have a contingency happen. And I want to tell you something. If there's something you want to take away from attacks, it is that in our analysis, with and without real-time contingency analysis, what we realized is the system is far more vulnerable if you did not do real-time contingency analysis. Real-time contingency analysis forces you to operate a little bit more conservatively. Far fewer lines are close to working at line limits, so they're less likely to be pushed over the boundary in an unobservable manner. So I want you to remember the way we've done this attack is that you cannot tell what's the line overflow. So we built our entire Java-based platform, commercial grade, right? Because we're working with the industry. We took Tom Overby's Texas synthetic system, which has about 2,000 buses and about 1,125 loads. And they also provided us with the hourly load data for the entire year of 2016, right? And here is a clip of what happens when you run this through the operations of the system. Effectively, on the x-axis, what I'm showing you is what the system observes is the load on every line, the power flow on every line. If I have attacked and changed the data, the physical load, after having changed the data, is on the y-axis. So what the system does not see, what it sees is about 91.5% load, or 6%, is actually 112% line loading. Okay, so I can cause a there may be a contingency system. I can exploit the contingency to cause a line overflow by changing loads in the system, but making it unobservable that you will not see it in the cyber system, but it's actually happening in the physical system. That's pretty concerning. But at the heart of all this is the notion that I can redistribute loads by changing measurements. Okay, now you do know that load estimators in the system, especially at the aggregate levels, have flags for large loads. But I'm not changing one single load to 20 or 30%. I'm going to change a bunch of loads in, maybe a bunch of loads associated with a large digital substation. Okay, and that I do not think we have the technology right now to assess, to the best of my knowledge. So we can ask the question, can you actually improve current state-of-the-art bad data detection, which is really intended to throw out noisy measurements and not really look at data that may look different from normative patterns. So what you need are data-driven algorithms, broadly what we call machine learning algorithms, that can actually identify these kinds of attacks, and you can look at it in a different context, also anomalies, right? An impending anomaly in loads can also be detected by these kinds of algorithms. So I'm going to give you, in the remaining 30 minutes of this talk, two approaches. The broad philosophy is that you leverage copious amounts of historical load data that power systems operators have been collecting and storing, right? A lot of this is trustworthy. Quite a few of it has metadata with labels, right? Maybe related to weather or other events. And then what we can do is we can take the incoming load data, because after all, state estimator always has a load estimator. Without the load estimator, you cannot run OPF or SCED. So you have an estimate of your current load. Can you use a machine learning algorithm to somehow compare it with your historical data to suggest that these incoming loads look very anomalous to what you would expect at this time of the day, this time of the year, month, week, based on historical patterns? So we're going to do it in two ways. One is a simpler, relatively simpler way using nearest neighbors. It's what is called a semi-supervised setting, and I'll talk about that in a minute. And another combines both a prediction of what you expect the load to be and a classification of whether this load looks anomalous or not. Okay, so these are our two attack detection approaches. So let's start with nearest neighbor detect. The broad philosophy here is as follows. What we're going to do is we take, so you've just finished state estimator, you have a load estimate, and that's your vector Li. Okay, it's at time I, it's a bunch of n loads in your system. I'm sort of going to describe the detector design as I describe the detection itself. What we're going to do is we store our historical load patterns, and we take this load that comes in and we compare it in, say, just simple L2 Euclidean distance with all our historical load patterns. And you could just restrict, if you have a lot of data and a very large network, restrict your historical load patterns for this time of the year, this time of the month, for example, right? And you're going to find a load pattern in the historical database that's closest to the current load pattern. What you would have done a priori with the historical data in training, that you would have split into training and historical data, is to come up with a threshold tau that tells you that below this threshold, you're pretty much operating in this class of normative load patterns. And if you're above this threshold, you could call it attacked, or you could just broadly call it anomalous, right? The key idea I want you to take away is I do not train on any attack data. This is why it's semi-supervised. I only have data that is not attacked. All right. Now this works quite well if you have a 30 bus system like I'm showing on the left side. Normative data patterns pretty much look like the blue points. As you increase the load shift for your attack, right? When you design these attacks, you want to have a minimum or a maximum load shift. So these are maximum load shifts. So, and if you put it up to 15%, it stands out. But if you did it on a larger system like the Texas system, there's pretty much a variation and there's a lot. If you use the entire vector, you will not be able to detect these anomalous changes in loads. So we came up with a slightly more enhanced version of this algorithm that I just presented. And the enhanced version is to say, let's group loads by a bunch of, radius RG, which could be like RG nearest neighbors. So you're going to look within groups of loads to see if there's an anomalous behavior. So for example, if you had a 3 nearest neighbor and bus 4 has the largest load, you start with bus 4 and take its 3 nearest neighbor. It's 3 hop nearest neighbors, right? Turns out bus 9 has the next largest load, but since it's already included in the first group, you skip it, and then you go to the next largest load, which is say bus 3, and then you take its nearest neighbors. Okay, you can have overlapping sets on these groups, right? So you can also upper bound the number of such groups you formed, and we upper bounded at 35 for the Texas system. So what do? Within each group, now, for every group, you take the subset of your estimated loads for that group and compare it with the historical data for that group. All right, you find the closest distance, and you then check if that closes. And so in your training phase, and I'm going to talk about training in a minute, in your training phase, you would have come up with a threshold, and you're going to compute that threshold, and you're going to do this for all the groups and sum the total number of groups that have violated the threshold. Okay, all right. So then how do we evaluate the efficacy of this algorithm? We use 2 very standard ROC parameters, the misdetection fraction and the false alarm rate, right? So misdetection is, so when I train this algorithm, I do not use attacks. When I test, I take the existing system and I create attacks on. So the number of attacks that were flagged as normal divided by the total number of attack cases is misdetection. Therefore, the probability of detection is 1 minus that, right? False alarm is the total number of cases that you flagged as attacked, which were not supposed to be flagged as attacks, which means because they were normal, and divided by the total number of normal cases. Okay, so as you vary the threshold, your false alarm rate changes, and therefore your misdetection rate changes, right? So we plotted our ROC curves, and I'll show the curves to you in a more 3-dimensional way. Okay, let's briefly talk about how we actually did this training and testing. So we took our entire bulk of historical data, right? And we break it up into 3 sets. You take all the data that you have effectively. You break them into 3 sets. 1 set is test, which is a small set, about 10% of the data. 20% of the data is training, and the rest is all historical data. So this way you're capturing enough of the system knowledge that you have, right? So for each group, you're going to compute this distance with respect to the historical data from your training data set, right? And then what you do is you compute a threshold. You're going to take the maximum distance in your training data for that group, and then you can scale the distance up. Maybe you want a little bit of margin. You allow for loads to still vary a little bit from the maximum distance from that particular historical data set, and that is your threshold. Right? Effectively, this is equal to saying that, because this is a L2 distance, like, a deviation of a certain amount is tolerated. Okay. How do we actually test this? We take the same 8754, 1 year's worth of data from Texas, hours of data. We look at those parts of we actually create attacks on the base cases for which you can actually, you have some level of congestion, and then you create this attack, and I'll talk about the attack in a little bit, but there are these optimization problems that we can set up as a bi-level optimization problem to create a post-contingency violation attack or a line overflow attack, right? It could be a line overflow without post-contingency, or it could be a line overflow with a following a contingency. So that's what we do here. We have what is called a post-contingency line overflow attack. So in every one of these hours, you can actually have attack data. So what we do is, the way we do this is testing is also done in a k-fold manner. This is really validation, if you think about it that way. So it's done in a k-fold manner. So the block that you test, you're going to rotate over these blocks, and these are all chosen at random, right? So your testing data will have both the unattacked data and the attacked data. Okay, all right. So how do our results look in this case? What I have at my disposal when I design the attack is the amount that I allow these, in this load redistribution attack, how much do I let the load shift change at any bus? So we went from 0, which means no attack, to about 15%. Okay, 15% of that bus's nominal load, right? So what we've plotted here in this 3D kind of plot is, this is our load shift, and then we pick a false alarm rate that we can tolerate. So we went from, say, 0 to 3% false alarm rate. And what this plot shows you is, how does the detection probability look? So the way to interpret the detection probability is, so when you have a very small load shift, obviously you're sort of going to still remain in this cloud of historical data, right? Even if you increase your false alarm rate, your detection probability improves, but not very much. But as you start increasing your load shift, your detection probability gets better and better, and by the time you're past 10% load shift, your detection probability is quite high. Now, what does this load shift mean in terms of consequences to the system? Keep in mind, our attack is designed to have a consequence, and that consequence is the line overflow. So for every load shift, every attack designed with a particular load shift value, there can be a consequence. And one of the things we know is that when you have very small load shifts, there's not going to be much of a consequence. Okay, so in fact, our line loading goes up from, say, 90% here, that's what you're seeing, to about 112%, right? So when you're just having very small increase, so these attacks were designed to cause an overflow on a particular line. So this is aggregate over all those attacks. That's what we're plotting here, right? So for all attacks that cause 100, slightly above 100%, sorry about that, slightly about 100% for a particular false alarm rate, what is the detection probability? And what you're seeing here is that most of these are green through yellow. So if you go back and look at the previous, you see that these very low load shifts really just don't even cause an epsilon change in loads, line loading. They don't affect it. So the overarching message is that you can have small load changes that may not be detectable, but those are not going to be at all in any way dangerous to the system. It's not going to cause, at least in the context of line overflows, not going to cause any effect on the system. So the most important attacks for line overloading are these attacks that can be very well detected. Okay, so that's the long story short, and this was a semi-supervised learning method. And immediately you come to the point where you ask, okay, so I have all this historical data, I can compare with it, I can see how close it looks to normative, and then I can flag. But what if I could even predict what the normative pattern should be based on incoming data and trained on historical data, and then look at whether the current estimate that you have fits in that category or not? All right, so we're going to use support vector models to do two things, right? We have load data. We're going to use a bunch of historical data to train a predictive model, as SVR support vector regression, to do load prediction. And then we take our observed loads for this time instant, and then use the predicted loads to actually do a classification. And then you can come up with a label that says this is anomalous or this is normal. right? A big advantage of this is that you can train each of these modules independently. You can make the modules complexity as you wish. And two most important things is that the predicted loads, and I'll show you, can be used if you worry about this current load not looking so good or the estimate not looking so good. Maybe you've lost observability for other reasons, and maybe you rely on this estimate prediction. You could use it both for attack mitigation and also for general system operations. So I'm talking even from a broader viewpoint, right? One of the things that this result shows us is that there's a great deal of interest now in going beyond aggregate load forecasting to bus level load forecasting. So this is a method for doing that. Okay, so let's briefly take a minute to look at support vector regression. What's the idea in support vector? This is actually a form of linear regression in the sense that you have a weighted combination of functions of your features. And I'll tell you what our features are in a minute. Obviously, they're going to be related to all the historical load we have. And your prediction is some kind of an affine function of your the features that you're using. All right. So the goal here is to have the prediction be as close to the ground truth as possible. So you want it to be within a margin of plus minus epsilon. Now this margin can be violated for any one single load. So you introduce an eta j. These are your sort of slack variables. You want to minimize those. And the regularization in SVR and SVM is to actually find a weighting model that does not overfit on the outliers, so you actually minimize its Euclidean norm. The question then becomes, how do I pick these kernel functions phi? And they are hard and they could be infinite dimensional, right? So the equivalent way to do this is to map it to the dual space. So in the primal space, our parameters are actually the weights as well as the bias, and these little slack that you're going to allow beyond the margin for every data point you have. So this is a supervised learning setting. You come in with a bunch of features and a predicted value. You use that to learn the model. The model you learned is W and B in the primal space, and it's equivalently alpha and alpha prime in the dual space. These are the Lagrange variables that come from these inequalities that you have to make. Right? So you have n alpha and alpha variables based on the n historical data that you're using to fit. And once you have this sort of correlation matrix, you come in for any new data point, you plug your historical data and your new data point in, and you compute this, and voila, you get a prediction. Now, SVR is very well known. There's this beautiful paper by Smola and Sholkov on this. And here's what we did for our data set. Where did I get the data from? I took the publicly available PJM hourly zonal load data. There are 20 zones in all. And then they have 3 years of data, 4 years of data from 2015 to 2019. So we use the first 3 years for training and the last year for testing. Right. So what were the features that we used? So at our H+1, this is what you want to predict. You will use the following information. We use time, it could be month, weekday, weekend, and the hour itself, right? And just the immediate hour. So in the past S hours, you take all the, S could be anything, it could be past 1 hour, 2 hours, 3 hours, as well as the past D days. So I'm gonna make this smaller so I can, yeah. In the past D days, you take the hour you want to predict and the previous hour, right? So these are all the features we use. We can also predict a load not just based on its own historical data for the last few hours and days, but you can also use other loads data, and we do that. We capture the spatial correlation between loads by doing that, okay? Very broadly, you can use this to predict bus level load data in any system, right? So what are our SVR measures? We're going to use root mean squared error and maximum absolute prediction error, all right? So here are our models. The first model, it takes the past 3 hours and the past 2 days, and there's no spatial correlation, so every load is predicted from its own load's history, all right? This is the least training time. The next model, we take past 3 hours and past 2 days, but we now include a spatial component. That means every load forecast or prediction is based on not only its own load's history, but also all the loads in the system. In this case, it was small. It's just we took these 20 loads and we mapped it to the 30 bus system, which has 20 loads in it. So it worked out. But if you're in a large network, you might want to take the 20 nearest loads, for example. And the last thing we did was we took 4 past hours and 3 past days, and we also included the spatial model. And you can clearly see that our training time exponentially goes up, right? We trained all this using scikit-learn. It's a Python package. And these are all the parameters we use. And we use a radial basis kernel, that should be kernel, right? So here are our results. So on the left side is the RMSE histogram plots or comparison plots. And on the right side is the MAPE comparison plots. And this is for each one of those 20 loads. Now we could dive deep into it, but in the interest of time, I'll give you 2 takeaways. The 2 takeaways were that having spatial correlation does improve your error. It lowers your error. But having a larger and a more complex model with like more hours and more days does not really, I mean, for this particular training data in this network, this is our optimal sweet spot was model 2, 3 hours, 2 days past, and spatial correlation. Okay. Now that we have a predictor, let's look at how the detector works. So here we're going to use support vector machine to do classification, right? So what are our features? So in this notation here, your features are the loads that come in, right? For all your historical data, you have a label. That's the ground truth, attacked or not attacked. In this setting, we're not doing semi-supervised. We will have some kinds of attacks, and I'll tell you about that in a minute, okay? What do we want to learn? We again want to learn a predictive, a classifying model. And what is our classification model? Basically, our classification model is going to look at, you know, this particular W transpose phi plus BM, it take the sign of that, and that's really whether if it's positive, then you're on one side of the plane. If it's negative, you're on the other side of the plane. Keep in mind, we're not doing in the simple linear space. We've actually projected into a high dimensional space. So we're taking linear combinations of nonlinear functions. It's always better in these problems to work in the dual space. And so the whole point is you can view this as a margin, right? So you want your ground truth to match a prediction. And so you want it to be non-negative always. So you can have this margin for every data point, and you minimize your margin and you minimize your magnitude of your weights to make sure that it's not overfitting to the outliers. Map that into the dual space. You basically get now again a sort of a covariance matrix here, right? And this is what you will use then to predict your incoming new data for which you do not have the ground truth. Okay, all right. So now that I've set it all up, I've built this, what am I going to test against? I'm going to test against 2 types of attacks. How do I design these attacks? I should have told you about it earlier, but I'll tell you now. So we've done a lot of work for the last several years on actually designing sophisticated attacks that are still feasible. And the way to do this is you know, in this talk, we're assuming the attacker has complete knowledge of the system topology. It can be done with limited knowledge, but nonetheless, the attacker has a goal. It wants to maximize the power flow on a line. It has a limit on how much it can shift the loads on all the buses. It also has a limit on how many buses it can change the measurements on. The attacker can do this by itself, and that I would call a cost maximization attack, just the upper level of the problem. But an effective attack is one where the attacker actually maximizes the flow after it has changed the measurements. The measurements have gone through the system. It's gone through contingency. And the contingencies have been placed in the second level optimization, which is really a DC SCED. So the outcome of the SCED should should be such that in the physical system, without the load changes, there's actually a line overflow. Okay, so these are the two types of attacks we consider, and we can solve this. This is what's called an attacker-defender bi-level linear program, and there are very clean and nice ways to solve it, and we have results work on that as well. What we've done here is that we took the PGM 20 loads, we mapped it to the 30 bus system, which has 20 loads. Okay, and what these attacks do is, these two types of attacks don't behave the same way. They actually redistribute loads in different ways, because in the cost maximization, you really don't know how the system is going to respond. You're sort of just taking a guess and doing it. That may not lead to actually violations at all right, or post-contingency violations. So here are our feature selections. These are predictive loads and these are observed loads. We train the detector. How do we train the detector? Our predictor is already trained. It just uses historical loads, okay? Predictor does not need any attacks. But for the detector, we use the normal data, but we created random load redistribution, because what we wanted to do was we did not want to bias this towards one class of attacks that we may be designing. What we wanted to do was to create a class of all kinds of arbitrary load redistribution. And we can just write that as a little small optimization problem. It's subject to a load shift constraint, and it's just random. So we just say Gaussian distributed attacks. So that explores the entire attack space, right? So then we test the performance on both random attacks and our intelligently designed attacks. So our intelligent design attacks are going to be either line overflow or cost maximization. Okay, all right. So to create a random attacks, as I told you, you take the true loads at any instant in time from your historical data, and then you randomly pick K loads to change, and then you randomly pick a load shift, and then you repeat this, and you can get about 10,000, 100,000 attacks. Okay. How do we split our data? Training data is 80% of the normal data and 80% of the random attack data. Okay. The remaining data is used for testing. All right, again, here we use scikit-learn package, which is a Python package with, again, the radial basis function code. Okay, all right. One important thing for us to do is how do we balance false alarm and misdetection? This is important because this determines how we pick the smallest load shift. Okay, so we picked our smallest load shift as about 1%, and in another case, we picked our so when you pick a smallest load shift to be 1%, your load changes are so small between an attack and the historical data that these planes are harder. When you move this to 5%, you can actually see that the delineation becomes better. Okay, all right. So here, in the interest of time, I have about 5 minutes, so I'm going to quickly tell you what's happening here. We created attacks with load shifts as small as 2%, going all the way up to 8%, right? And on the x-axis, you see the minimum training load shift that we needed. And on the y-axis, on the two sides, in blue, we've plotted the misdetection rate, and in red, we plot the false alarm rate. So the smaller the load shift, the worse the misdetection rate. So it is. So you do not have a good detection probability. The larger the load shift, and this is for the minimum load shift that we're going to pick, right? For any choice of false alarm, this is what you will see. Okay. Just want to tell you one thing. When we do SVM and SVR, we do have I'm sorry to go back for a couple of seconds, just bear with me. When you go back to SVM and SVR, for example, this is SVM, the classification, this C matters, all right? So when you give C a very large value, you're basically saying that you cannot violate this constraint. You have to have this margin, and you have to work beyond this margin. So when you do that, that is actually going to enhance your performance, but it also puts more weight on outlier detection, okay? So our results are always functions of this constant C. It's a parameter C, right? So here, the C is also called the outlier penalty factor. as the C increases, I tolerate less deviations in my detection, right? The margin. So as a result, the larger the C is, the better your detection probabilities. In this case, we picked the smallest load shift as 3%. But the larger the C is, the longer it takes for you to optimize, the longer it takes for you to learn the model. So there's a trade-off here. All right. So this is the last of my last few of my slides. Let's look at this. So on the left side, what I have is my load shift percent. I changed all the way from 1% to about 20%, right? I look at all possible attacks. These are random attacks and cost maximization attacks, as well as line overflow attacks, all right? For very small load shifts, you see the same story as before. Your detection probability is not very good. As you jump to around 5% load shifts, your detection probability really is nearly 100%, okay? This is all for a fixed false alarm rate. On the right side, if you look of all these attacks, you look at the attacks with consequences, attacks that have a line overflow, right? So the line overflow attacks have been designed, right? And they can have a very small consequence. Their detection gets better and better as the load shift increases. And the same is true for the cost maximization attacks. Finally, I'm going to leave you with this little observation. So I have two plots here, and you should be asking me now, hey, you talked about a prediction model, right? The detection model obviously is using the prediction model, but what if you could use suppose you figure out there's something anomalous, what if you could use the predicted loads in the place of the actual loads to run OPF? Your attacker does not know you're going to do that. Your attacker changed the data, and they're waiting with excited in glee to see this overflow happen, right, in the physical system. But your anomaly detector, which is based on SVM and SVR, tells you that data pattern looks anomalous. That would have been, that particular data pattern would have led with increasing load shift to have this physical power flow on the left side. If I go back in and put the detector, I can actually thwart most large load shift attacks. Very small attacks, the difference is so minimal that you can't do very much. Similarly, you can do this for line overflow attacks. You can do it for cost maximization attacks. You can actually even do better. Because the attacker was intending to increase the cost, it's a slightly different optimization problem. So you can actually lower your cost by just doing your predicted value, because that's really your expected load profile at this point. So I think with this, I am done, and I'm open to questions.
Thank you, Lalitha, for the very interesting and very insightful presentation. Anybody can unmute themselves and ask questions. I will take the first hit here. Just to summarize two questions that I have seen that a lot of people are asking in the chat. We have only 15 minutes. If we cannot answer all the questions, you can follow up offline with Lalitha to answer any further questions. So the first question I have seen asked by 2 or 3 people here has to do with the assumptions behind the attack. So do the attackers require to know information about the Jacobian matrix, the H matrix of the system? Do they need to access which measurements and which locations of the system? Because you have framed this as the false data injection attacks as part of a load redistribution attack. And I think there are questions, how this is framed and what are the assumptions for an attacker to access those measurements and locations and which parts of the H matrix?
So the right way to think about these kinds of attacks is that this is not going to happen with some 2-bit hackers. These kinds of attacks can really only be done by nation states. At that point, as has been done in other contexts by nation states, at that point, without having sufficient knowledge of the system, at least bare bones, you cannot do this. And if you go on Google Maps, you can find quite a bit of generation information, where the generating plants are and so on. And so these kinds of attacks do require some kind of insider information. So from that viewpoint, I think I I believe that I don't need to make a very strong argument for how much topology knowledge, how much, indeed, this is what keeps our system secure, that that level of knowledge is not accessible to everybody. But if some kind of a nation state attacker wanted to get this, it'll be naive to believe that it cannot be done. So that's how I would, I'm so sorry. I thought I already told you you can record the talk. So I don't know if you recorded, but.
Yeah, I did. So thank you for the answer. I hope answered some questions. If not, the people that had these questions can unmute themselves.
Yeah,
the second
chat box, but and they are all welcome to email me later too if they didn't get. Sorry.
That's great. So the second question I have seen twice or three times appear in the chat has to do with the threshold. Does your system and the work that you have done is kind of adapts the threshold based on the system conditions or the network configuration and the topology of the system, or is it a static threshold that needs to be changed every time you train your system?
Okay, so I'm so sorry. I got a little distracted by some of the questions. What do you need to? Are you saying is the detector itself, does it need to be trained? Is that what you're saying? So
the question has to do with the threshold. If your threshold for detection adapts to the network configuration, the topology of the system, and the system conditions.
That is correct. So the right way to look at this is, I mean, for example, most operators do planning at least a year in advance, and that planning sort of tells them, has a broad sense of what kind of lines may be taken out at different times of the year. You could take this model and do it for different times of the year. For example, you could have detection thresholds for fall, summer, spring, winter. You could have detection thresholds for different weeks. You can always just tailor this very precisely and broadly for your system at hand. Indeed, your topology will change, and that can change how your loads are. In fact, you may not even have all the loads in the system. That should be the case, but if topology changes, some things can change. But if the loads in the system don't change, as long as you can create these groups even based on time of the year, you can always use more and more metadata to design a better algorithm. That's all I'm trying to say. So these can be tailored to do as appropriate. And I noticed that Anurag wrote that it should be called false load redistribution attacks. Yes, sure. And I noticed Junbo also wrote that he's done some work on compromising. We too have done Junbo. Yeah, so there's a lot of work now on just using local measurements to design attacks. Sorry, I won't look at the chat box. I'll just listen to.
I think we're really going into an era where we're talking about false data injection attacks, low redistribution attacks, demand side attacks, mad IoT botnet attacks, right? So it comes into a time where all these attacks, in one way, they're interconnected. What are the assumptions and the threat modeling one makes in order to address them in a systematic way? So another question I see here in the chat from Fei Teng has to do, can we directly use state-of-the-art forecasting model in order to do detection? State-of-the-art models from forecasting societies, and what are the new requirements and challenges on forecasting techniques when we use their outcomes in order to detect attacks? Okay,
so state-of-the-art forecasting models, to the best of my knowledge, are for aggregate loads. The key difference here was that you're actually predicting loads at the bus level. So, I mean, you could be a PJM operator with like 500 zone or 20 zones, but you could, if you dive in, you may still think about 100 or more buses are important at the transmission level. So this goes beyond just those forecasting at the aggregate level. To the best of my knowledge, there's not that much forecasting at the non-aggregate at the bus level. So that's what this does. Now, I have not done a state-of-the-art comparison because, that's just like a rabbit hole you can keep going down. If there's interest in implementing these things, then you get to the point of enhancing and improving. This is academic research. This is a proof of concept. This is an idea to show that we can both predict loads at the bus level. For normative operations, you can look at anomalies, which includes cyber attacks. What we've tested as an anomaly here are cyber attacks. So Christian, in that context, asked me, why not use precision and recall? You use precision and recall when you train on an unbalanced data set. So if for the first problem, the data set is all of one type and you do nearest neighbors. For the second problem, I can actually generate as many attacks as I can generate historical data. So it's a great question, but it's not really an unbalanced data set. I'm just not training on a very specific class of attacks, which is the right thing to do because you do not want to overfit on a specific class of attacks. I'm training on a very broad class of random but load redistribution attacks. All right, sorry, go ahead, Harris.
Another question, I see two questions actually, they kind of correlate, you know, the work with reality. I think you partially answered that where you mentioned about, you know, open source intelligence by nation state actors, you know, finding locations. But the other part of another question I see is how realistically feasible you know, your design detector is if you base it on DC state estimation versus AC, you know, because, you know, ISOs, you know, transmission operators mostly use the AC state estimation. So can you comment on that?
Yes. In fact, DC can always be detected. Gabriela Hug had some papers on it. We had some papers on it relative to AC. And so what we've done in our Java-based platform, it's all AC, it's not DC. I just set up the initial problem as a DC problem just so you understand the attack. Everything we've done is based on AC state estimation. It's based on attacks designed for an AC state estimation system. So this is really important to know. What we assume is a DC power flow, optimum power flow, or a SCED with the DC optimum power flow, but that's still the norm in the industry. So we're not actually doing anything unusual there. Good question. So in fact, these attack designs as well as mitigation strategies are based on AC state estimation, not DC. I want to make that very clear.
Thank you, Lalitha. Another question has to do with the time scale. Let me find it. So at what time scale do you detect the anomalous data? So maybe the question can be seen at what time scale do you expect data measurements to come in? Do you assume, you know, the traditional SCADA measurements coming, and at what scale do you detect them?
So you are, very good question. So this sort of goes back to the slide I had. If you bear with me for a moment. Right. Yeah. So this is literally saying SCADA data comes in. Typically, when you poll SCADA over all the instrumentation, they claim that you can get it within 4 seconds. In fact, what delays use of SCADA data is the amount of time contingency and SCED can take for large systems, say like the PJM system. It can take up to 4 minutes. Maybe really fast systems, maybe up to 2 minutes. So that's our model. The amount of time it takes to do dispatch and then go back in. So the attacker has up to every few minutes to update the attack. If the system hasn't changed too much in that amount, in a window of 30 minutes, the attacker can replay. Every time it gets the SCADA measurements, it adds the same attack. Once you've designed an attack, adding measurements is very easy. You just keep adding the measurements and go from there. Now for AC state estimation-based attacks, the attacker has to quickly estimate the state. State estimation is much faster than SCED, for example. Is this all realistic? Not entirely clear. I actually want to leave people here who work in power systems with the notion that I do not believe these things, the grid is vulnerable. At the same time, would you have ever believed that you would have wildfires and a pandemic and et cetera at the same time? Fact is stranger than fiction. And in that context, when cyber attacks happen, and this has been always true in the history of networks, when cyber attacks happen, they always have an Achilles heel that they exploit. So in that context, one must assume that an attacker could have pre-computed a whole bunch of measurements, assuming some normative model for the measurements, and then just keep adding it. Sure, it's not going to be ideal, but can still be very good. Because Under normative conditions, grid does not change very much. Operations, things can be taken out, things can be done, but even if you give me an hour, I can actually take an hour's worth of data from the previous day, create my attack measurements, and push that in. So I can do sort of like a replay attack, but with the intelligent redistribution of loads. So it can be done.
Exactly. Yeah. Okay, thank you, Lalitha. We have 3-4 minutes. I'll go to another question. Hopefully we can answer all of them. So how do you differentiate, Anurag had another question about this earlier, so I passed it by mistake. How to differentiate by load changes in the system? Because essentially your false data injection attack focus on how, you know, a load redistribution attack. So how do you differentiate by, you know, normal load changes in the system and, you know, load changes that are caused by false data injection attack? That is, I think, another interesting question here.
So I mean, our work, so normal load changes in the system are never going to follow this rule of thumb of load redistribution attacks that there's no net load change in the load. No net change in the load always leads to a very interesting, this is why we use the word redistribution. By definition, a redistribution with no net load change is a false load attack, Anurag, because you asked me that question before. Any other load redistribution can actually happen, right? You can have a brownout in one place, so that does change your load, but it does not redistribute your load. It just changes your load in your system. So that anomaly is significantly distinct and different from cyber attacks of this class. I cannot make a claim about cyber attacks of a different class that I haven't thought about yet. So what I can say is that these models can certainly maybe tell you that something is not normative for this time of the year based on the SVM and SVR, but it can also tell you that because you've trained on random loads, it can all random attacks, load redistribution attacks, it can also indicate that this could possibly be an attack. Because certain load patterns will not happen even if you had a problem with the failure in the system and so on and so forth. I don't think so, but I could be wrong. I don't think you would have a no net load change. It may happen, but with very small probability.
I see. Yes, yes. Okay, thank you, Lalitha. And the last question, we have 1 minute, is can you comment a little bit about the feature selection stage in your learning-based algorithms that you have used for the detection?
Yeah, I also see something on how do you not overfit, right? Those are great questions. So again, I'm just going to go dive down into that part. This is where those parameters matter a lot. Right? So this is support vector regression here to avoid, so almost always in SVM to avoid overfitting, you do this regularization where you regularize over the squared Euclidean distance of your weighting model, right? The choice of M in SVR will determine how much you want to overfit or not overfit. All right, if you make M very large, you will allow for a greater slack or a greater error in each one of these predictions. That's actually a good thing. So you need not overfit. If you had a lot of data, it's okay to fit well. But if you have less data, you want to make sure you do not overfit. So the same thing is also true here in the SVM, in the classification model. And this is where I was talking about this, the outlier penalty coefficient, right? Because ultimately what you're doing here is if you take this in a product, you want it to be greater than 0, then you're correct, otherwise you're wrong, right? And depending on how you pick lambda j for every one of them, and then how you modulate that lambda j with the C, if you make C very large, you're really enforcing a stronger penalty on making the right decision. If you make C smaller, you enforce a different penalty. And this is how you can adjust. This is pretty standard in SVM and SVR to avoid the overfitting issue. Plus these regularization of the Euclidean distance. Very standard things.
Thank you, Lalitha. I think we hit the time. We're exactly at 1 hour. We passed 1 minute. I think at this time, we would like to thank you for giving this talk in our task force. If we didn't answer all the questions to you, if Lalitha did not answer all the questions to you, I'm sure she will be more than happy if you follow up with her if you have any questions about her existing work.
Yes, I'm delighted by these questions. It's actually amazing. Thank you for the interest and the interactions. Email me any question. I unfortunately do not put the list of all my papers, but I have a humongous list of papers in this area from attack design to detection. And I'm very, very happy to. Here's my email. I'll just put it in the chat box. It's lsankar@asu.edu.
In the meantime, concluding this webinar with Lalitha, I would like to remind you that we have the recorded videos of the presentations in our website, cmt.ieee.org/pscps, and you can also put your email there so you can get the emails about the future announcements. And with that opportunity, I would like to say that our next webinar will be on September 30th. By George Stefopoulos from New York Power Authority. So with that, we'd like to thank you for joining today. Thank you again, Lalitha, and have a nice rest of your day, everyone. Bye-bye.